Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts like guidelines for Thevenin's theorem and their application for analysis of series and parallel resistive circuits excited by independent voltage sources, power, and energy in such circuits. Slide 1. Thevenin's theorem. To begin, let us understand what Thevenin's theorem is. Thevenin's theorem is a fundamental tool in circuit analysis. It tells us that any linear circuit made up of resistors and independent voltage sources can be simplified to just two elements, a single voltage source in series with a single resistor. This pair is called the Thevenin equivalent circuit. Now let's understand each part. Thevenin voltage, often written as fifth, is the open circuit voltage measured at the two terminals where the load is connected. Open circuit means no current is flowing, we simply measure the voltage. Thevenin resistance, written as RTH, is the resistance looking back into the circuit from the load terminals, but with all independent voltage sources replaced by short circuits. That means we consider their internal resistance only. This theorem is valid only for linear circuits, meaning the circuit's behavior doesn't change with changes in voltage or current. The theorem simplifies the analysis by reducing complex networks into a simple form, which is particularly useful when we want to study the effect of changing the load. Example: a network of a 12-volt battery and two resistors can be simplified to a 9-volt Thevenin voltage and a 4-ohm Thevenin resistance, making analysis much easier. Slide 2. Steps to apply Thevenin's theorem. To apply Thevenin's theorem, we follow a specific step-by-step method. Step 1. Identify the portion of the circuit where we want to find the current or voltage, usually across a load resistor. Step 2. Remove this load resistor from the circuit. This helps us isolate the rest of the circuit for simplification. Step 3. Calculate the Thevenin voltage, which is the open circuit voltage across the terminals left after removing the load. Step 4. To find the Thevenin resistance, deactivate all independent voltage sources by replacing them with short circuits, and calculate the resistance across the same terminals. Step 5. Now draw the Thevenin equivalent circuit, a voltage source equal to fifth in series with resistance RTH. Step 6. Reconnect the load resistor to the simplified Thevenin circuit. Step 7. Finally, use Ohm's law to find the current through or the voltage across the load resistor. This process not only makes calculations easier but also helps understand how the circuit behaves when the load changes. Slide 3. Application in series resistive circuits. Let's now see how Thevenin's theorem applies in a series resistive circuit. A series circuit has resistors connected one after another, so the same current flows through all. The total resistance is the sum of all resistances. When we apply Thevenin's theorem to such a circuit, we simplify the network to just one voltage source and one resistance. This is extremely helpful when we want to study how different load resistors would behave if connected across two terminals of this network. For example, consider a 10-volt battery connected in series with two resistors, 2 ohms and 3 ohms. Without doing complex analysis each time, we can simplify the circuit to one voltage source of 10 volts and a total resistance of 5 ohms. If a load resistor is then connected across one part of the circuit, we only need to analyze the current using simple Ohm's law. This method becomes especially helpful when the load is changing frequently, such as in sensor systems or variable resistor applications. Slide 4. Application in parallel resistive circuits. In a parallel resistive circuit, all resistors are connected across the same two nodes, so the voltage across each is the same, but the current may differ. Applying Thevenin's theorem to such circuits also simplifies analysis. For example, suppose we have a 12-volt supply connected across two parallel resistors of 6 ohms and 3 ohms. Instead of working through parallel current and voltage calculations, we can find the Thevenin equivalent circuit across the terminals of interest. Thevenin voltage in this case is simply the voltage across the open terminals, which would be 12 volts since voltage in a parallel branch remains the same. Thevenin resistance would be the parallel combination of the two resistors, which is calculated as 1 divided by RTh equals 1 divided by 6 plus 1 divided by 3. Solving this gives RTh equals 2 ohms. Once the circuit is simplified to this form, we can easily calculate the current or voltage across any newly connected load. Slide 5. Power and energy in DC circuits. Let's now talk about power and energy, which are important when analyzing any electrical system. Power, represented by the symbol P, is the rate at which energy is used or delivered in a circuit. In DC circuits, power is calculated using the formula P equals V multiplied by I, where V is voltage and I is current. Energy, represented by A, is the total amount of work done. It is calculated using A equals P multiplied by T, where T is time in seconds. In a resistive circuit, power can also be calculated using the formulas P equals I squared multiplied by R, or P equals V squared divided by R, depending on what quantities you know. Thevenin's theorem makes it easier to calculate power delivered to a load. One especially useful case is when maximum power transfer is required. This happens when the load resistance equals the Thevenin resistance. This is called the maximum power transfer condition. Example: a 4 ohm resistor connected to a Thevenin equivalent circuit with fifth equals 12 volts and RTh equals 4 ohms will receive maximum power. Using the formula, we can calculate power easily. Understanding these principles helps in designing efficient systems, avoiding energy loss, and optimizing performance. Slide 6. Advantages and limitations of Thevenin's theorem. Let's understand why Thevenin's theorem is so important, and also what its limitations are. Advantages. 1. Simplifies complex circuits into a simple equivalent form. 2. Makes it easier to study the effect of changing loads. 3. Saves time during repetitive calculations for different load conditions. 4. Helps in power system design and analysis. 5. Essential for understanding behavior across load terminals. 6. Assists in maximum power transfer analysis. 7. Reduces errors and confusion in large circuit networks. 8. Applicable to both DC and AC circuits, as long as they are linear. Limitations. 1. Thevenin's theorem works only for linear circuits, where current is proportional to voltage. 2. It does not apply directly to nonlinear components like diodes and transistors. 3. Dependent sources need special steps for calculation. 4. Complex networks may make fifth and RTh calculations difficult. 5. Magnetic couplings and transformers cannot be simplified using Thevenin's directly. 6. Requires both open circuit and short circuit analysis, which may not always be easy. 7. Thevenin's model is less intuitive for current-driven circuits. For that, Norton's theorem may be more suitable. So, while Thevenin's is a powerful tool, it should be used correctly and in the right situations. Slide 7. Differences between Thevenin's and Norton's theorems. It's important to know how Thevenin's and Norton's theorems compare. 1. Thevenin's theorem represents the circuit as a voltage source in series with a resistance. 2. Norton's theorem represents the circuit as a current source in parallel with a resistance. 3. Thevenin voltage, or fifth, is the open circuit voltage at the terminals. 4. Norton current, or in, is the short circuit current at the terminals. 5. Thevenin resistance RTh is the same as Norton resistance Rn. 6. Thevenin's form is used when voltage is the main driver. 7. Norton's form is used when current is the main driver. 8. Both are equivalent and can be converted into each other. Fifth equals in multiplied by Rn. 9. Choosing between the two depends on what type of source is present and what is more convenient for solving. Understanding both forms gives flexibility in circuit analysis and helps in applying the right tool for the right problem.